Hi, everyone, and welcome to Adams. I hope you're doing well and are ready for another round of tutorials. It's about time, I think, that we put our freshly acquired Python skills into practice and try revisit some parts of the lecture. This is the first of two tutorials on neural networks, basic feed-forward neural networks. And today we will have two sort of parts in this tutorial. Very much as in neural networking, there is on the one hand side understanding how they work and how they produce forecasts. It's a supervised learning technique. How do neural networks produce forecasts? We will in stage one or phase one, as you can see here, go through the corresponding steps, basically setting up a neural network. But it's not all about forecasting, or it's not all about producing forecasts. The key thing is that we need to train our neural network very much as any other learning algorithm. We need to fit it to some data, and that's part two of making it work, where we essentially look into backpropagation. If that term should be new to you, then you probably want to have the lecture on neural network training and its video before going through this tutorial. So essentially, what we do here is to revisit the neural networking foundation lecture and the neural network training lecture. And once you've went through these two lectures, you are clearly ready for this tutorial here. And actually, when you go through it, you will notice that there is quite a lot of explanation, quite a lot of text again, also some pictures. Let me give you some context. Normally, the tutorials are delivered by my PhDs, and we realize that it's often useful if somebody else reintroduces a certain concept. So that it's not only me or only the lecturer introducing some concept, but that you also get a mini presentation, let's say, from one of the tutorial speakers. And this is why these tutorials revisit quite a bit of concept that I also covered in the lecture. And this semester is all a bit different. So I will basically move over the conceptual parts in the tutorial because it would be again me explaining you the concept. A concept such as what is softmax? Oops, sorry about that. Or a concept like what is an activation function? And we did discuss that in the scope of the lecture. So I think it's most useful if I try focus on the key Python bits. All right, with that disclaimer, it's time to get going. So let's have a look. Um, to set up this neural network, we will, for now, stick to some structured data. But given that later on we want to do NLP, where we typically face classification problems with many different classes. Classes as many as all the words in a language. So we often use neural network to solve multi-class problems in practice. And so I wanted to move away from the credit scoring data set that we've used before. And instead, there is a data set on Kaggle, which is useful for the tutorial, or which basically provides us with a multi-class problem. It's a data set on apps and their popularity in the App Store. You can download the data from Kaggle, see this link here. It's good to have a quick look at the data on the Kaggle website because there, let's take a quick look. You would also find a data dictionary and some information, some context about this mobile app store data set. My internet seems to be a little bit slow today. It's Labor Day, so probably everybody's on Netflix. Maybe that's why. Here is the data set from the Apple Store. We have a bunch of columns, 17 in total. One of these we will use as our target variable. And here you see that Kaggle will also, on the homepage of the dataset, provides you with some basic EDA stuff so that you can get an idea about it. However, as usual, you will find a version of the dataset also in Moodle in our download forum. So easiest way would be to get it from Moodle. And the version of Moodle is different from that one. I went through a bit of data preparation. If you're keen, a good exercise might be to download the data from Kaggle and then have a look at this little Python script, which you also find in our GitHub repository, which basically does the data preparation. It's not a great deal, really. So, but if you want to follow the data prep steps that I implemented, have a look at this script. Otherwise, if you want to straight jump into the tutorial, you can download the prepared dataset, which is Apple Store _ prep from Moodle. I'm loading that here, and here's a little overview. We have a name, of course. So this is Pacman Premium is the first one. Then we have Evernote, say organized, WeatherBug, etc. As information, we have the size of the app in bytes. Not sure that is particularly useful. Price, rating count total, and let me scroll a little bit to the right. There are also a bunch of dummy variables in their data set, which type of genre this app belongs into. Is it a productivity type of app? Is it a shopping type of app? Social networking app? What type of app is that? But don't worry, if you're not particularly interested in the data set, we won't look as deeply into it as we did in the credit scoring data set in the previous tutorials. I'm using the name as my index. So after this little operation here, app, which is my data frame, set index, I could index individual apps, or if I like, using their name. So I can index rows using the name if I want to. And then here is the data again. It's mainly numeric data, floats and ints. The ints are predominantly dummy variables. And if you scroll down, in the end, you find user rating. And this variable will serve as our target. So setting could be that we try to predict the popularity of that app in the App Store, given these characteristics like what's the price, what's the main primary genre, what is its size, although I would not know how this drives popularity. Anyway, and in the original data set, you would find 11 or so different classes, different ratings. But in my preparation, I decided, because some user rates are very rare. In the original data set, there exists a rate of, let's say, 0.5. You could give an app 0.5 stars, but virtually nobody did that. So many of the rates were very sparsely populated. Because of that, I decided to reduce this 10 or 11 class problem to a 6 class problem where we have rating grades from 0 to 5. You see that these grades are still rather unevenly distributed. The vast majority of apps was rated 4-star. A few 5-star apps we've got, and then 0 also sticks out, and that's quite common with ratings. Ratings normally display a U-shaped distribution. That is to say that you have a reasonably large amount of ratings that don't like an app or a product or a movie. And also you have a large amount of very good ratings typically, and then you have the U-shaped, and an average rating is very rare. And if you, You see that a little bit also in that data set. But due to my pre-processing, the U shape is a bit corrupted. Anyways, so we want to fit a classification algorithm to that data. We want to build a neural network. And by just configuring our neural network in the right way, we can easily accommodate these 6 different classes, or as many classes as we would like to have. And well, I was warning you a little bit of explanation how we move on from logistic regression to neural networks, how we could also use a linear type of model. Look at this matrix notation here, how we could use a linear type of model in order to predict the rating grade in a regression setting. And then a regression setting, note this picture, it's similar to the ones I'm showing in the lecture, mimics neural networks, are very simple and shallow neural networks. And that's the type of structure we will soon set up. We have 35 input variables, covariates in the dataset. They give us the input layer of our neural network. Then we will soon decide on a number of hidden units in the hidden layer. And the output layer, well, that is determined in this setting to be 6 because we want to distinguish 6 classes, user rating from 0 to 5. And each of the output neurons or output units of our neural network is then to model the probability of an app belonging to that class, belonging to that group, receiving that user rating. That is the idea. Some more explanation and some notation being introduced. We will use an activation function in the hidden layer. So we will go beyond logistic regression and add some nonlinearity by having an activation function in the hidden layer. You will probably remember that there are 3 common choices for activation functions in the scope of neural networks, which are the sigmoid, the hyperbolic tangent, and the ReLU function. And well, you've seen that before, but let me quickly run through this code. We thought it's maybe a good idea to remind you how these functions look like. This is the sigmoid with its characteristic S shape, and the graph also shows us the derivative of the sigmoid and how the derivative is bounded by, well, 0.2 to something. I think this is 2.5. We have the hyperbolic tangent with its derivative, and there we also have this S shape, but it covers a larger interval, not 0 to 1, but -1 to +1. Also, the derivative is a little bit larger, which will prove important once we train our neural network. And last, there is ReLU, which sort of emerges as the activation function of choice because it has certain desirable properties. And we'll use this function, we'll use ReLU later on in the example to add some nonlinearity to our data, because obviously that is a nonlinear function. Okay, so our 3-layered neural network features 2 matrices with weights that together make up the 3 parameters that we need to train and that we need to estimate. And well, in this picture, the corresponding notation would be that we have 3 layers, and their values we could denote by A prime, and A double prime. B for biases in the hidden layer, V for biases in the output layer, and then capitalize W and M as our weight matrices, connecting the input layer to the hidden layer and the hidden layer to the output layer. And with this notation, which is mainly because we sort of like that graph here, you could write down the mathematical equations of your neural network in matrix form by saying that the weight matrix times the input A plus bias put through some nonlinear activation, gives you the output of your hidden layer, gives you A prime, and then the final output of your neural network would be this A prime times another set of weights, M, plus another bias, V, plus some added, well, nonlinearity, S, which for classification will be the softmax function. So this S is to represent softmax. And we can, of course, depict that also as a nice matrix, just to make sure we really understand what's going on. And these type of equations or these types of matrices, the tutorial is all about coding that in Python to fully understand really what's going on inside a neural network. And this is why we basically have this picture here, so that you remind yourself, okay, we have this combination of linear algebra, weights times inputs plus biases, and then add some nonlinearity to it to obtain a structure of latent features, which here would be our A prime. We can consider these latent features, and from these latent features, we would then derive a forecast by feeding them through another bunch of weights, adding biases, and applying another activation function. And you will remember that for neural networks in classification, the nonlinear function we apply in the output layer is always a softmax function, where we essentially take the raw output values of the neural network. You could think of the raw output values as, well, let me quickly go back. I think the picture is most helpful here. The raw output values of our neural network would be the latent features that we produce in the hidden layer with A prime times weights plus bias. That's the raw output, the score. And we would obtain one output score for each of the output layer units, 6 in our app rating case. But these scores are just numbers. And normally we want these numbers to represent probability estimates. And this is what softmax ensures. Once we put our scores through this softmax function, we will have probabilistic forecasts. And well, we can run through this little demo. This is why we implemented it in the first place. If you imagine that you have a neural network with 1, 2, 3, 4, 5, and 6 units in the output layer, and you have put some data into this neural network, one example with some covariate values, and the neural network delivered you these raw output scores. Then just putting that through softmax, which is easily implemented using NumPy, you can convince yourself that as a result, you get some probabilities. And just looking at the scores, by far the largest score we have here in the last element, 0.21, and correspondingly, this entry carries the highest likelihood or has the highest probability after a softmax normalization. And you can easily convince yourself that these scores also sum to 1. And that means that our output layer now gives us a nice probability distribution over the 6 classes that we have in our problem. And for each class, we can take the model estimated class probability estimate from the output unit. That's also the essence of this picture, which is quite nice, I think. And it reminds us of the calculations in any feed-forward type of neural network. We have an input, we have a linear model, or this algebraic type of piece, wx plus b, that gives us some scores, latent features if you wish. We add nonlinearity to these features. That gives us another set of latent features subject to some nonlinear transformation. And then These we can put through softmax in order to get probabilistic values, probabilities, probabilistic forecasts. And with these forecasts, we would then be able to calculate the loss of a multi-class model using cross-entropy. Okay, time to see some more code. We have a little more than 7,000 cases in our data. We can also look at a single example. We will actually focus on a single example, very much on a single case today. That would be one app. We have the covariate values, its price, $1. And actually that's Mahjong. I'm sure you know that app. And we do see that this app got a user rating, which is our target, of 4, as most of the apps in that data set. And remember, the unique values in our target variable are these different user ratings, and there are 6 of them. Now, that is our target. So we have multiple classes, and these are consecutively numbered. So here comes the first bit. When we want to use this target variable for our neural network, then we need to do some coding here. And if you remember the structure of the cross-entropy loss that comes later on, it's actually very sensible that we encode our target as a dummy matrix. If we have 6 classes, we should encode Y as a matrix with n by 6 columns, because then we can easily calculate residuals and the cross-entropy loss functions in particular. An easy way to do this is using a utility function from Keras that is called toCategorical. We put our output into that function. Let me change the code to make it a bit more explicit. So we feed that our target variable, which is currently just a bunch of numbers. And then we get this one hot coded structure, dummy Y, and that's something we could readily use for neural network learning. And that's also what we need to do or will do in the next tutorial when we start working with proper deep learning libraries. That's exactly what we then need if we do everything the proper way and want to train a neural network using cross-entropy loss, which, spoiler alert, today we won't. I also put a little bit of code here. We are a bit lucky that our classes are just numbered. In a multi-class problem, classes are often labeled, so they carry text labels. My example is credit rating analysis, where you know how rating agencies like Moody's or Fitch give corporate borrowers, big enterprises or sovereigns, rating grades that express their creditworthiness, where a grade of AAA would be the best grade and indicating the most trustworthy type of borrower. And should we have such labels as our multiple classes, AAA, AA, B plus, B minus, these sort of labels or text labels, then we couldn't really use this toCategorical function. And that code here, if you wonder why that is here, it shows you a new class, label encoder. That's the standard workflow that you have when you set up a neural network. You first encode your labels, whereby this label encoder is not more than just numbering all the different classes using consecutive integers. And then once you've done that, you can use these toCategorical functions to get your one hot matrix. That's just a standard workflow, and this is why I wanted to introduce it here in the tutorial, since we are already with coding our classes, concerned with coding our classes. Okay, a little bit more of housekeeping, data reshaping, and conversion. And we are pretty much set up right now. We have data of the apps, 35 variables and 7,000 cases. Same number of cases, obviously, for the target variable and 6 classes. And this is the type of structure. Also note that both X and Y are stored as a NumPy array. That is the type of data structure we'll use a lot in subsequent sessions. That's the type of data structure that deep learning libraries like Keras, for example, which we will use, or same with TensorFlow, what they want to receive. Very often you can't use a data frame or something and put that into a model, but need to work with NumPy arrays, but that's okay. All right, so let's set up our neural network. This is basically my configuration. The number of covariates is given. 35 covariates we have in this data set, so our input layer has dimensionality 35. Nothing to decide here, that's given. And the same holds true for the output layer, because we want to predict 6 distinct classes. We need 6 units in the output layer. That's just the way how we set up classification networks. C output units for C classes. Each unit has the class-specific probability then, or estimates the class-specific probability. The only real choice that we have is how large we make the hidden layer, or in a deeper network, how many hidden layers we want. And well, I choose it to be 50, could be any other number. Indeed, since my input layer has only 35 covariates, that's quite a large hidden layer here. Normally, you would not have more hidden units than input units in many feed-forward neural networks that approach some prediction task. You wouldn't have that structure. But it doesn't matter much for this tutorial. Play a little bit around with these numbers if you fancy. It's not dramatically important. And then we have our neural network again here. Just for now, we'll assume a proper setup, meaning that once we compute the forward path, the output of our network will be probabilities. So we take the raw output scores and put them through softmax. So there's like a softmax layer here, depending how you interpret the network graph. That's the output unit. And if you interpret that to be the final output, then before, as shown here, you would have a softmax layer that takes care of the normalization of your forecasts for you. And these dimensionality, this is important, and this is what I want to focus on when we now try and configure our neural network. To that end, we need weight matrices and biases. And these weight matrices, before we train them, we need to initialize them somehow. You could do that entirely randomly. For M and V, these two weight matrices, sorry, I keep saying V, that's wrong. It's obviously W. Apologies for that. So for W and M, you could just pull random numbers of the right dimensionality. If the input layer has 35 units and the hidden layer has 50 units, W has 35 by 50 dimensions. And for M, we would have 50 by 6 dimensions. Or that would be the dimensionality of M. And we could just draw random numbers, but this is not going to work too well. If you just sample these numbers, these weights for the first forward path, if you initialize them with random numbers, let's say random numbers from a standard normal distribution, since you sample a lot of weights, 35 by 50, right, for example, there will be a bunch of weights that are quite large, maybe above 3, something like that, if you use the standard normal. And then you might remember from the lecture that you will easily run into the saturation level of your neurons, depending which activation function you put. If you use a sigmoid activation, for instance, sigmoid is most vulnerable here, you will easily end up in this range where sigmoid maps the input always to an output of 1, because the sigmoid function is pretty much flat and equal to 1 for larger input values. And if the weight is too large, you will end up in this saturation level. And this is what you typically don't want. I'm making use here of a rule of thumb, how to initialize your weights using a uniform distribution with certain boundaries, and many tutorials, and also this paper by Glorot and Bengio recommended that we could use this little formula here, the number of incoming plus outgoing connections, 6 over that number, square of that, as our boundary. And then initialize the weights such that they are uniformly distributed with values somewhere in that boundary. And this is what we're doing here. I'm fixing the seed of my random numbers generator. That allows me to basically repeat the calculations. When I now sample my weights, I first set up this limit, the recommendation or this rule of thumb, and then I sample the weights input to hidden, weights hidden to output, and my two bias vectors using NumPy random uniform. So I'm using a uniform distribution between plus limit and minus limit. And these functions from NumPy random allow me to specify the dimensionality of my matrix that I want. And this is the first part where we have to be a bit careful. For the weight matrix input to hidden, that is W, or hidden to output, that is M, we have to ensure that we use the right number of rows and columns, that we select the right dimensionality. And this is why we set up these variables, hidden layer, input layer, and output layer earlier on, which carry these values. All right. Just for the point of changing something in that notebook, using shape, you should know the shape function. You can easily convince yourself how your weight matrices and your bias vectors have the right dimension. Since I'm using ReLU activations, the recommended approach toward initializing the biases is to set them all to 1 when using ReLU, or 0 when using sigmoid. But I use ReLU, so I choose np.1s and get a vector of the dimensionality of the hidden layer 50 or the output layer 6. And this is how I get my vectors, which later on we need to train. But for the first application of our neural network, we need some numbers to make it work. And we'll feed our neural network with one case from the dataset. Remember our Mahjong app with all its values here. And we now simulate the forward path. And there is one thing I want to, it's a detail, tiny detail, but it can be quite annoying. We have one example from our input data from our matrix, this app, this Mahjong app. And well, you don't see it here, but if you find out the shape of that data point, NumPy stores data as arrays. And NumPy is designed to work with multidimensional arrays. So the focus of NumPy is not so much to be the go-to library for linear algebra, where often enough we deal with vectors or matrices. The focus in NumPy is more to also have generalizations of the concepts that we typically learn in the scope of our algebra lessons at university, have these concepts generalized to higher dimensions. So NumPy would allow you, for instance, to transpose a tensor of 6 dimensions. And obviously, you know how to transpose, what transpose mean in the context of a vector, where you change a row vector to a column vector. And of course, you know what a transpose operation is about in the context of a matrix, where you kind of exchange rows and columns. But what actually is transpose when you have a 6-dimensional tensor? What is that supposed to mean? That's the type of thinking in NumPy. And what you see here is that our data point, our fixed app in our matrix, Mahjong, NumPy stores that as a one-dimensional array. And you see that here, 35, comma, nothing. That's a 1D array in NumPy terminology. And the only reason I'm stressing that is often you have to change that. If you want to do if you want to use a neural network, or if you generally want to calculate something, if you work more in the mathematical realms of vectors and matrices, this 1D array is not going to work. You cannot easily do a dot product with that. Or, well, actually you could, but the result might not be what you expect. And often you will have to do some reshaping. So look at that bit here. I'm taking this 1D array, x5, and then I'm reshaping that into a proper vector of 35 by 1, of dimension 35 by 1. So now I have a column vector that I can work with. And typically you really do have to do that yourself explicitly. There are some mechanisms in place. It's called broadcasting. If you use this 1D array in a context where it can't be a 1D array, but has to be a proper row or column vector, broadcasting would ensure that the computations work out somehow, but or might work out somehow, but that's often enough not what you want. For instance, you would never make a column vector out of that. Broadcasting would always turn that into a row vector, which could break your dot products when you calculate dot products or something. So just mind these reshape operations. You see them very often, and you will need them very often yourself when you perform such tasks. Always keep an eye on the dimensionality of your data. That is extremely important in the scope of networks. Okay, so now we have our input. The variable is called input. Could have called that x. And I'm also extracting my target, where I basically have the same issue. By default, I would get a 1D array of these 6 numbers, and I want that to be a column vector. Therefore, I have to reshape my data. And then to sum that part up, here's the overall structure of our neural network. We have weights from input to hidden layer, W, of dimensionality 50 by 35. We have our input data, which is 35 by 1. Weights hidden to output with dimensionality 6 by 50. And finally, our target, which has dimensionality 6 by 1. And it's obviously not crucial to set up these vectors and matrices in this way. You can have row vectors where I might use a column vector. Just when you calculate the forward path, you have to make sure that the dot products work out and are actually defined. So let's have a look. We first calculate the hidden layer input, which is x times the w, or here with this type of data structure, we actually calculate w times x. And then we add a bias to that. That's the input of the hidden layer, or the hidden layer input signal. And the hidden layer output signal is then the added nonlinearity, which we achieve by using the ReLU function. Now we can look at our shape. So this 50 by 1 is our hidden state. These are our latent variables that we obtained in our neural network, from which we will, in the next step, derive some forecasts. So let's move on to the output layer. The output layer, our inputs, we calculate once again by multiplying the weights with the output of the hidden layer with our latent features. There are 50 by 1. Our weight matrix M, it's M, sorry, I'm trying to stay in the picture I was showing you earlier on. There, the weight matrix was M. M is 60 by 50. So multiplying that works out. We're calculating the dot product. We're adding a bias. And then we have our outputs. And obviously, these outputs don't look like probabilities. You can think of them as the input or the output layer input. If you keep this picture of a neuron as a computational unit that has a left part and a right part, where you have the input, which is basically previous layer outputs times weight plus bias, and where you then apply some function in order to translate the input activation and get an output activation. Then this concept also applies to the output layer, where we could put our output layer inputs. It's really a tongue twister. Anyways, we take this with signal, this vector here, put it through a softmax function. I defined softmax earlier on, so if you wonder how does that gonna work, where is softmax defined, I have a custom function earlier on which implements the softmax operation. And then we get our probabilities that almost sum to 1. Some rounding issues here, but that's close enough to 1 to convince ourselves that with the softmax, our output of the neural network is a probability distribution over these 6 user ratings. Yeah, and then we have, this is our output, right? Our output probabilities. And here's our true target. And unsurprisingly, again, if you look at this vector carefully, you will notice that that's a user rating of 4 stars, which was the by far most prominent class in the dataset. So the true class is 4, and therefore we would like our output to be 0, 0, 0, 0, 1, 0. That is the ideal output. And instead, our output is, well, 0.05, 0.27, 0.11, 0.50, 0.01. So that's very bad. because the true class, which is the second to last here, has a probability of maybe 2% if we are generous, and it should be 100 or as close to 100 as possible. So it's a very poor forecast. But, well, we just initialized our weights randomly. We cannot hope to have a better forecast for now. To get better forecast, we need to train these weights. And soon we will. But that's basically just the basis here. That's why we go through that. That is the basis to compute cross entropy, which also might have been a new concept in the course. That's also the next part. Here's the cross entropy loss function once again. For the multi-class case. And if you look at that, that is, oh, sorry, that's the, we're deriving cross entropy here. I was a little bit confused. That's actually the entropy, which is sort of the building block. And it's a concept that has its origins in the field of information theory. It's very important in signal theory. And this function, the entropy, well, I don't want to go into too much details, but it allows you to calculate the number of bits that you need to encode a certain piece of information. Hence, information theory. It has to do with transmitting information, maybe over a network or something, and then how do I encode a piece of information? And in our code, well, the information we try to encode is of what class is one of these apps, where classes are our user ratings. And then you have cross entropy, which extend the concept of entropy and assumes that you have a sort of wrong mechanism to do the encoding. And it's the number of bits that we would need if we try to encode the true symbols y using this wrong mechanism, and we can call that y hat. And cos entropy by definition is always bigger or equal to entropy. And if you look at the cross entropy function here, and remember that y actually is a one hot vector, you see why we have set it up as a one hot vector, because for all but the true class, this will just cancel out. This product will cancel out because of multiplying with 0. And then what basically remains is the logarithm of our forecast minus 1 for the true class. The logarithm of our forecast for the true class in the case of our example, Mahjong, was 2% roughly. And the log of that minus 1 would be our loss. And we can just work that out by multiplying these bits because we have our y hat nicely coded as a one hot vector. And just as a little excursion, you might remember the Kullback-Leibniz divergence, either from other lectures or maybe from business analytics and data science, where we touched on it in the scope of the uplift session. It's a very popular measure to quantify how similar two distributions are. And it turns out that the Kullback-Leibniz divergence is actually the difference between the cross entropy and the entropy. But onto neural networks, for us, that's going to be our loss function. That's cross entropy loss. And this bit here, as I said, we need to sum over all the possible classes, but thanks to our coding, we don't really have to do that. We just can multiply our actuals with the log of our forecasts and immediately get that loss at least for one single data point. I left a little example here just so that you can really walk through the computations if you wish. It's a toy example that has nothing to do with our neural network and our data. It's just showing the calculations, and you can play with these if you want to familiarize yourself with the behavior of the cross entropy loss, but only if you want. For our neural network, just once more, that is our label, that is our prediction, which is bad enough. And here we can really easily calculate the cross entropy loss for our neural network with this little sum here. Because, again, I can't stress it enough, because we use the one-hot coding for our multiple classes. And here you really see why this coding makes a lot of sense. And then we get a value. The result of that summation is an array. And I'm using here this item function, which NumPy offers to pull out the actual value from that array, not arrow, sorry. Just that you see what I mean. L by default is this. It's stored as an array, although it's actually a scalar value. It's not stored as a scalar value. It's always an array in NumPy, but I can pull out the scalar value using item. And that would be basically the quantity that we need to minimize when we want to improve our forecasts and when we want to train our neural network. And if you like it even better, you can do it maybe more elegantly even, because since we are still having this sum here, we can get rid of the sum and use a dot product instead. The advantage would be that the dot operation is highly optimized in NumPy and similar libraries. So that way here obviously gives the same result, but it would be faster. We can't test that when using a single example, but if we would have a large vector of forecasts, then using this little time stopping trick I was using in tutorial 3, I guess, or was it 2? I don't remember. You could show that the dot product is more efficient. So that would be the preferred way to calculate cross entropy loss. Okay, and this loss we can minimize, of course, only by adjusting our weights and biases, because these are the only 3 parameters in the neural network. And you will remember that we do that by gradient descent, meaning that if this is our neural network, that's the cross entropy loss, right? And our forecast is the result of applying softmax to the output layer inputs, which we calculate by using the hidden to output layer weights M and multiplying these with our latent features, the hidden layer output, and adding a bias plus V, where the hidden layer output comes from using a ReLU activation and applying that to the hidden layer input, which is basically W times X plus bias. Looks a bit overwhelming, I know, but it's really this typical chain that we have in neural network. Data times weight, nonlinearity, with ReLU. And then another chain of data times weight plus nonlinearity. And this is how neural networks work. And also that shows us how it's just a nonlinear regression that we are calculating here. It's nothing but a nonlinear regression. And in order to train this using gradient descent, we need the gradient of the loss with regard to the parameters W, M, B, and V, which you can understand that this big vector, typically very big, the parts of which then store the partial derivative of the loss with regard to the input to hidden layer weights, the hidden to output layer weights, and the two bias vectors. And these we need to produce. And you can guess what comes next in this tutorial. We're going to get there. I'm pulling a maybe nice animation. If you like animation, that's a nice animation here I found on the web, integrated using this GIFI tool here, which basically shows or gives a visual intuition how gradient descent work. You have seen similar graphs in my lecturing slides, how we are trying to find this local minima here by making update to our current set of weights and biases. And if you are a bit unsure here with gradient descent, I left one example where we are not using gradient descent to train a neural network, but instead we use gradient descent to, well, optimize a very simple function, just this quadratic function. Found that at towarddatascience.com, this example, and slightly changed or polished it for the sake of this tutorial. Have a look at that. It's super easy to do gradient descent with this example. It's maybe useful to do it with this simple example because the overall step is just the same. We need to work out the gradient, and then we do the update of our weights in the opposite direction of the gradient, using this update rule that the new parameters are the old parameters minus the learning rate times the gradient. And minus make sure we go in the opposite direction of the gradient, which points in the direction where our function increases the steepest. So this is the direction where the function increases in the steepest way, and we move in the opposite direction of the gradient, very much as this little ball here, and hope that we eventually find a nice local minima. We will try to do that right away in our neural network. Okay, so that's our function again. But for the sake of the example, I realized that I better make several simplifications. Well, I'm a bit mean to our beautiful neural network. Bear with me. It's to keep the code simple enough for your first manual backpropagation. This is where this is going to end up. What did I change? For multi-class problems, we use softmax. Unfortunately, the derivative of softmax is a little complicated, and I didn't want to go there. So the first change that I made is that I said bye-bye to my multi-class problem, and instead we will approach our user app rating modeling problem in a different way. Somewhat as if we were using a regression type of model. Note this change here. Instead of having a softmax layer, which translates the input to the output layer into the final output of the neural network. Normally, we do that with softmax. I wanted to simplify the thing, so I use ReLU. Why do I use ReLU? Um, well, we could have used the raw output scores. We don't need to perform any or apply any function in the output layer of the neural network. And in regression, we normally don't have any activation function in the output layer. We just put out the raw output scores coming from the hidden layer output times weight plus biases. That works well for regression. But my network still has the 6 output units. So what do I actually hope for with these output units? And I will interpret these 6 output scores of my neural network as the confidence of my model of my network, how much a user will like that app. So it's not a probability because I don't use softmax, but it's still a score which indicates somehow, where larger values indicate that a certain rating category has higher likelihood of occurring, and smaller values indicate that a rating category has less likelihood of occurring. And then noting that user ratings are strictly positive, or zero or strictly positive, well, zero or positive, it makes actually sense to use the ReLU function here because it's guaranteed to give me an output that is lower bounded at 0. But the main point again was to get rid of softmax and its slightly complicated derivative. You'll see how this simplifies the code a lot in a minute. Okay, so now we try to train our neural network. First of all, we will do one step, and then we really do backpropagation thereafter. But let's start small. When we want to train our weights, when we want to do gradient descent, we need to find this gradient of our loss function. Oh, by the way, sorry, forgot that. I also changed the loss function to squared error because that squared error function has this beautifully simply derivative, which is just the residual. And cross entropy would also add a little bit of complexity as its derivative is not as nice as that of squared error loss. So here, note that two here we have squared error loss, y minus our network forecasts, which are just confidences, if you wish, but not probabilities anymore. And then we want to find the derivative of the loss with regard to our parameters, w, m, v, and b. And we start with m, the weight matrix between the hidden and the output layer. Right, so here comes the chain rule. There are two derivatives that we need. Well, we need more than two, but these two are we will implement as functions. The derivative of the loss, which depends on our network output and the actual target variable, output and y. And for squared error loss, it's just output minus y. And it's good to point out that this function is to calculate the derivative of the loss with regard to our forecast. No matter what loss function you employ, you will need that function that calculates its derivative. So for cross entropy, it looks more complicated than for squared error. This is why I'm using squared error. But the idea that we need this loss is generic. We always need this derivative here. And also we will need the derivative of our activation functions, which for ReLU is very simple. You have seen it before. I'm just re-implementing it here. And well, would our neural network also incorporate sigmoid activations, we would also need the derivative of the sigmoid here. And similarly, we would need the derivative of softmax, which I wanted to avoid for simplicity. All right, so let's have a look. First of all, that is all copy-pasted here. That bit of code is all copy-pasted so that we can just remind ourselves of the structure of our neural network. And also the name of the variables I'm using. And I'm hoping they are somewhat intuitive. We have inputs and target. Our target is just, and our input is just one example. We stick to Mahjong, this app. Then we have the hidden layer inputs, which we calculate as the dot product of the weight matrix W times the input plus the bias, specifically the bias input to hidden. The hidden layer outputs are our nonlinear activation of that input, so ReLU of HL inputs. These are our latent feature values. We multiply them with another bunch of weights hidden to output using the dot product, and add a bias hidden to output. That gives us the raw output scores of the neural networks. And the raw output scores of my neural networks in my example go by the name OL underscore inputs, output layer inputs. Not sure if that was the optimal choice. Maybe next year I use a different name. Anyway, now I use that one. And the final forecast, the output layer outputs, I calculate for simplicity using the ReLU function applied to the output layer inputs, not softmax. In the forward path, we could easily use softmax here. In the backward path, that would be a bit more complicated, so we let it be. And this is then our network result. That is the full forward path for one data point through our neural network. And well, it reminds us that our model is very poor at the moment, because remember that the true output for this example was 0, 0, 0, 0, 1, 0. So we are nowhere near yet. But no wonder, we haven't tuned our parameters at all. Okay, now comes the difficult part. When we do the tuning, and at this point you might want to revisit the lecture slides where I think I have it open. Yeah, I have it open here. Where we sort of derived the update equations for a very simple neural network in the third chapter on neural network training. I suppose that although the notation is unfortunately slightly different here, I suppose that might help a little bit, or else what's also a very nice source, I think. Well, let me quickly scroll down for the hyperlink. The machine learning glossary has this entry on backpropagation, which I personally like quite a lot. My slides are inspired by that entry here, and that would also help you to follow what we're doing here. If you go through that, I recommend you having a look at one of these sources on top of the code. Right, let me go back. By the way, I'm using not Jupyter Notebooks today, but Jupyter Lab, which is well, slightly revised version of the Jupyter Notebook, and it has some nice extensions that you can install to make your coding experience richer. For example, here this extension where you can get a nice a table of contents for a notebook. I find that quite useful. Have a look at Jupyter Lab and maybe a Google search for Jupyter Lab and extensions. If you care about having a nice environment to do your coding, and don't use Colab, then try that out. Anyways, where was I? Here. Okay, so we need the derivative of the loss with regard to our hidden to output weights. And now we need to go through the computational graph in a backward manner to see what bits we need. And the first bit we need will be the derivative of our loss, which is the residual. And I can make use of the function that I was implementing earlier on to calculate that. And I denote that by dl, derivative of the loss with regard to dy hat, our forecast. And it's just the residual. And just looking at it, we see it's quite a big residual here. That was the first computational step when calculating the loss, comparing actuals to forecasts. Next, we need the derivative of our forecast with respect to the output layer activation. The derivative of our forecast was calculated. Our forecast was calculated as output layer input and the ReLU activation of that. That is how we calculate y hat. It's the ReLU activation of the output layer input. Let me go back to the equation. Here's the squared error loss, y minus y hat, and y hat we calculate as the ReLU function of our output layer input. And the backward path, I need the derivative of that as my next factor. The derivative of my forecast with regard to the raw output score. And because of the calculation, delta y hat by delta raw output or output layer input, that's the derivative of the ReLU function. Fortunately, I have it ready here. So the next bit I'm calculating is the derivative of my ReLU with regard to the, sorry, that's not right, output layer inputs. So I'm taking one step back in the computational path, going one step back in the forward path. Forward path, we had raw output score, ReLU activation, final forecast, and now we find the derivative of the final forecast with regard to the raw output score, and that's the derivative of ReLU with regard to the raw output score. Which looks like that. Okay, now the last bit we need, the last factor when we go through this chain, when we apply the chain rule, is the derivative of our output layer input, or what I call the raw output score, with regard to the hidden layer output. The output of the hidden layer was, that was basically just weights times the hidden layer outputs. And so the hidden layer outputs, that is our derivative. We don't need to calculate any function here. I think it's helpful to look at the equation again. Once we go deeper into this neural network here, we were dealing with the ReLU function in the output layer. And the next computational step is M times the hidden layer output. All that bit here plus V, but that doesn't matter at the moment. That bit here is the hidden layer output, and we multiply it with our weight matrix M. And since we seek the gradient of the loss with regard to m, the next factor is just the hidden layer output. I'm just restating the variable here, not doing any calculations. Once more, back to PowerPoint maybe, to be on the safe side. We're sort of doing this computation here. Gradient of the loss with regard to the hidden layer weight. We need the derivative of the loss with regard to the forecast, the derivative of the forecast with regard to the raw output score, and the derivative of the raw output score with regard to our weight, the one we seek at the moment. And as you also see here, the derivative of the loss with regard to the forecast is just the residual for squared error loss. Fortunately, the yellow part here, the derivative of the forecast with regard to the raw output score, is equal to the derivative of the output layer activation. That's the second factor we introduced. And the derivative of the raw output score with regard to the weight is actually the output that comes from the hidden layer. Right? It's this function here. Can you see the eyes? Yeah, you can. It's this bit here, the purple bit that I have highlighted at the moment. If we work out the derivative of O with regard to W2, that's just H. And that is what allows me to or that is what I have stored as the hidden layer output. Before moving on, oops, let me get rid of that. We now have all three factors that we need for our partial derivative. The derivative of the loss with regard to the forecast, shape of which is 6 by 1. The derivative of the forecast with regard to the raw output score, which is 6 by 1 as well. And then the outputs of the hidden layer, which are 50 by 1. And looking at these scores, you can make sense out of this calculation here. We're basically multiplying the factors together. Elsewhere in the lecture, I used a convenience operator called prot, where I was saying that, you know, when you have these factors that are matrices and vectors, and you want to multiply them together, somehow you need to make sure that the dimensions work out, that you apply the transpose where needed, do broadcasting where needed, etc. And when you write down an equation, it's nice to make use of such convenient functions, but if you code something, you really have to make sure everything is right. So here we take the derivative of our loss function with regard to the forecast, 6 by 1, 6 by 1, we just multiply that together. The result, obviously, because it's element-wise, is then 6 by 1. And when we calculate the dot product, we transpose our hidden layer outputs to have 1 by 50, and then everything works out, and our partial derivative is of dimension 6 by 50, which, if you think about it, is brilliant, because that is what we need. It's the same dimensionality as our hidden to output weight matrix. That's also 6 by 50 and has to be. Therefore, we will later on be able to calculate a nice gradient update, since our partial derivative and the original weights, they just match, and they must match. So basically, I'm just highlighting that when we code that manually in Python, we need to make sure that we calculate the product the right way. Next thing is the bias vector of the output layer, the gradient of the hidden to output bias. And actually, it turns out that that's quite easy and rather similar to what we did before, note that bit here. It's exactly the same as this bit, which does make sense because we would, in order to find this partial derivative, proceed in the same way. We would find our way backward from the loss function, from the residual, from the loss function, the derivative of the loss function, going to the, which depends on the forecast, going to the derivative of our forecast with regard to the raw output score, which depends on the output layer activation function, softmax, and ReLU in my simplified example that we calculate. And then we go back one step further, which would be checking how the raw output score, how the input to the output layer depends on our bias vector. And if we look at our bias vector, let's look at it. Here's B. So the derivative of that bit here with respect to B, that's just 1. And multiplying by 1, yeah, we don't need to take that into account. And hence the partial derivative of the loss with regard to the output layer bias is, well, the same as the partial derivative of the loss with regard to the, oh, sorry. Now I made a mistake. Apologies. We are currently with bias V. The same concept apply, but that was a bit confusing maybe. Apologies, forgive me. To produce the raw output score of our neural network before applying the final ReLU function, to produce that bit, we multiply the hidden layer output with M and add a bias. So what we actually seek, once we are done with this computational bit here, with this ReLU function, what we then seek is the derivative of our raw output score with regard to V. So the derivative of the now highlighted bit with regard to V, you see that this is 1. And since we use the chain rule, we only have to add a factor 1, which we can dismiss, in order to calculate the partial derivative of the loss with regard to the bias vector V. And then it's just the same part that we were computing before. Here we go. Now we have half of the gradient. What we need next is the partial derivative of the loss with regard to W and B, the weights that live in the earlier layer between the input and the hidden layer. There we have also bias vector B and weight matrix W, and we need their derivatives as well. So basically we go back and repeat the whole exercise. And at that point, let me show you the slide once more. At that point, you begin realizing that, hey, wait a minute, a lot of these computations here, they reoccur. If we take it now one step further in this graph and don't look for the derivative with regard to W2, but W1 here, then the first bits remain unchanged. We start again with the derivative of the loss with regard to our forecast, the derivative of our forecast with regard to the raw output score. That's the same bit. Then we have a minor change in the purple term. At this point, when we want to go back all the way to W1, we don't look for the derivative of the raw output score with regard to W2, but instead we look at the derivative of the output score with regard to H, because H is what depends eventually on W1. W1 drives H, but it does not drive W2. So that is the new term here compared to before. Before, look at the purple term. We had raw output score, its derivative with regard to W2. Now we have the derivative of the raw output score with regard to H. That brings us to H. And then we need to go on with H. And since H in this example is the output of the hidden layer, we need to find the derivative of that output with regard to the input of the hidden layer. And their difference is coming from the activation function. So the derivative of the hidden layer output, H, with regard to the hidden layer input, Z, turns out to be the derivative of our activation function, G prime of that, or ReLU derivative. And then we can go back one step further and ask, how does that depend on our weight W1? So we add delta Z by delta W1, which turns out to be the input. And well, if we later at this point ask how that depends on the bias in that step, that derivative, well, it's not shown here, apologies, but that derivative would also turn out to be 1. So we start exactly as before and multiply these two terms. And now we realize our example was not efficient. We should have stored the result of that computation much earlier. We have already employed that result twice. In both of the previous two partial derivatives, we used that product, this factor. And now we need it again. And in fact, you would need that again. If you had more layer, there are these recurrent factors and you need to cache them. And finally, I do that. I call that the output layer errors, which is just a common term for this ingredient here. You could give it, from a programming perspective, you give it any name you like, but that's a common term. And then we have seen that, I'm also doing some printing here, the next factor that we need to calculate the gradient of the input to hidden weight matrix, W, the next factor are the weights of the hidden to output layer. So we multiply these two, making sure that the dot product works out. Then you go one step further back at the network and ask, how does the output of the hidden layer depends on its input? That's this bit here. You use the ReLU derivative at that point with regard to the hidden layer inputs. And then final step, and note, were we seeking the gradient of the input to hidden bias, we would be done. Here, however, we take it one step further and multiply that result, which I'm updating this matrix here. So gradient input to hidden equals gradient input to hidden times ReLU derivative hidden layer inputs. So I'm adding the factors bit by bit. And here I'm doing the same. And at the original input data X, which we realized when looking at the PowerPoint, does also show up in our equation. That is just the input of the hidden layer with regard to the weight matrix connecting the input to the hidden layer, and that the partial derivative is equal to x. I left some print statements on the way so that you can convince yourself why I'm calculating the dot products in the way I do. And then in the end, we have this gradient, which has the same dimensionality as our hidden layer, of course, and that we can use in gradient descent. Soon enough, finally, the gradient of the input to hidden bias, that same computation as before, just we need one factor less. And so this is just another example where we were a bit wasteful and could have enhanced our code even further by storing that result or changing the computations a little bit. But that only affects the speed of the training and not the actual results. We are finally ready to do the gradient update, which is easy enough, really. Once we have done all the previous steps, once we did that, the gradient update is very trivial. We have the weights m between the hidden and output layer. So we take them and we subtract the corresponding gradient times the learning rate. And for the other parameters, we just proceed alike. And it does not produce any interesting output so far, but it worked out, which is good enough. It shows that, at least in terms of organizing the computation, everything is okay so far. That was, well, the first step toward backpropagation. We have calculated one gradient update, and we could now redo everything and calculate the next step. Soon we will, but I have better code for that, no worries. We did so far use a single data point, x5 in the matrix, the single app Mahjong, and we did the gradient update based on having seen only the single example. So that is actually stochastic gradient descent, what we calculated, because we were using only a single example to calculate our loss. Well, maybe we want to use batch gradient descent in subsequent tutorials, or even full gradient descent, where we go through all the training data. But that wouldn't change that much. In either case, we need to find the error. We can approximate the error based on a single data point, which we did. We can use a mini batch of data point, which we didn't do, but could have done. And we could also just calculate the residuals using all the data points in our training set, which gives us a better approximation of the gradient, but it's more costly. Okay, so in chapter 2.5, you have a slightly revised and improved code for backpropagation, setting up a learning rate. I'm also now setting up an epoch. Remember, since we update the gradient with every single data point, the epoch is the key parameter to determine how long we keep on training. One epoch means one run through the entire data set, which was 7,100 cases, 7,100 and a bit. An epoch means that we took all of these 7,100 and a bit apps, calculated the forward path, produced a network forecast, and updated the gradient, updated the weights afterwards using gradient descent so as to improve the forecast. We'll do so for 10 times. And then this bit is mainly, there are some minor differences, but it's mainly the same code as before. You also see this variable names bias, input to hidden, everything should ring a bell. And now I have it in the for loop. And yeah, that really is backpropagation. We first compute the forward path. We then collect the gradient that we need, collecting all the partial derivatives. And then we are ready to do a gradient descent step. We are ready to update our weights and biases, considering the current learning rate. And let's run that and see how it goes. Doesn't look too bad. We start with a very large loss because the weights, when initializing them, they were completely off. And we reduce our error bit by bit. Slightly surprised that this keeps on for so long. I might have forgotten to run this cell here. And previously I was playing with a counter of 100 epochs. I think I didn't run that cell. And when testing the notebook, I had 100 epochs. So this is, I think, why it continues that long. Yeah, it does. Oh dear. But anyways, maybe it's good. You see how with every epoch, your loss decreases, and the loss here, for simplicity, it's the squared residual. And slowly but steadily, we are getting there. 10 more, 7, 6, 5, almost done, almost done. And we are all looking at these numbers. We could go on because we are still making some improvement. But obviously, we have waited more than long enough. And give yourself a pat on the back. We just tuned our weights. We just trained our neural network using gradient descent, using backpropagation with nothing but NumPy, almost nothing but NumPy. So that's quite good. And if you want more, I left two hyperlinks here. If you just go to your preferred search engine, look for backpropagation tutorial NumPy, you will find loads of stuff. These two, I think, are pretty good in doing something what we did, what without the simplifications. The next step could be to reintroduce softmax, replace the squared error loss with cross entropy loss. Tutorials like that or that do this exist. Have a look if you are interested. If you only want to get the intuition of backpropagation, maybe that was enough. Okay, I'm realizing time is up. So in the reminder of the notebook, there is just a little bit of code to check the results. We are producing some forecasts for a fictitious test data set, apply our network here, calculate forecast for all the observations in the test data set by running the forward path again. That's not particularly exciting. And getting a confusion matrix. And looking at the confusion matrix, you might think that looks weird. And it does. But in fact, it doesn't look too bad because remember that in this funny data set, we had a rather imbalanced distribution of user ratings. And rating category 4 was by far the most popular. And rating category 0 also was pretty popular. And noting that many cases end up in these cells is kind of a good signal. It basically means that our network has learned that these two categories are the most important ones, and it has sort of put everything into these categories. It has pretty much ignored all the others, and we would need to keep on training in order to make the network smarter to know that some of these apps actually are not rated as 0 or 4, but receive some other rating. But to put that into context, the classification accuracy is 68. When you run that, maybe you're a little bit better. You can get values above 70%, but 68 is not too bad. And if you compare that, I added this little demo here where I would work out how good do you classify with random guessing classes. And since you have these 6 classes, random guessing is guaranteed to be pretty poor. And indeed, that would be your confusion matrix for a random guessing classifier. And that only has accuracy like 17%, which is close to what you would expect. So our tiny toy neural network is a lot better than that. All right. We haven't tuned the learning rate. I just put it to some values. I invite you to play with that a little bit. I think, albeit more explanation being available in that notebook, we discussed the learning rate sufficiently in class and what it is about. What we did not discuss in class is momentum. That is something you might want to have on your list. If you train in your network using momentum, it means that you alter your update equation. Vanilla gradient descent would basically be that bit that I have highlighted. That's how you update your weights, taking the old ones, then multiplying the learning rate with the gradient of the loss with regard to all the parameters. Now here, W would be all the parameters. And the last term, that's called a momentum term. We have another parameter. Mu. Mu is a bit like, it's like the learning rate. It's a kind of weight that you need to decide on. More interestingly, we have this delta Wi minus 1. Well, delta Wi is the change of our weight that we are calculating, and then delta Wi minus 1 would be that equation with dw I minus 1, and then in the momentum term, we would have I minus 2. So that is a recursive equation here. And what we are doing is essentially we are calculating a moving average. And if you have done some stuff in time series, you will notice that that's a exponentially weighted moving average, which we are calculating here, over previous updates. And that is what momentum kind of does, is tries to enhance gradient descent with some memory of what has happened in the past. How did we update weights in the past? Typically that works well and improves over ordinary gradient descent. So very often you will have an opportunity to set a momentum term on this lambda, this mu parameter, because an algorithm would incorporate a momentum term. And in a nutshell, you can think of that as a velocity control mechanism. When you reach a plateau in the loss surface, where there is not much going on, you can make larger steps because you want to leave that plateau. And when you, on the other hand, approach sort of cliff in the loss surface, then you might want to be careful because cliffs are dangerous. Gradients can get very large, and that can lead to bad updates. We discussed that in the lecture. So in such region, this term here, where you consider previous updates, will sort of hold you back a little bit. It will dampen the oscillations in regions of high curvature. That is the idea. I think velocity control mechanism is a good way to refer to that. That was a bit brief. If interested, have a search on that and look for a tutorial on momentum. Many explanations are available, obviously, either on Towards Data Science and other platforms, also on YouTube, whatever channel you prefer. And you'll see this parameter in future tutorials in the form of Nesterov momentum, which is like a state-of-the-art way to implement that. I have one homework for you. I'm not sure you know that channel, but if you're not, then this is maybe the most important lesson of this tutorial. But I also had the link in my slides, right? Make sure that you watch the 3 blue, 1 brown video on backpropagation. Actually, there are 2 videos. I'm linking only the second one, which is a bit more formal. It's wonderful stuff 12 minutes or so. If you manage to survive me, then these 12 minutes are very worth invested, and that will further substantiate your understanding of backpropagation and what's going on a lot, I believe. All right. Wow, I think that was it for today. We are done with yet another tutorial. Well done. We have done our manual backpropagation. So in terms of what's up next is that we'll make our life a lot easier and build neural networks using Keras, which is a high-level deep learning library. And that will make it a lot easier to build neural networks, train neural networks, and also the results that we can get from these networks, they will be a lot better than what we achieved today. But still, I think we achieved a lot. And I hope it has added to your understanding of the training of neural networks to go through the steps for once in this very manual manner. All right. So wish you a good day ahead. Take care and see you soon.